All right, let's dive into a really key concept in AC circuits. What exactly happens when you add an inductor? Understanding this is fundamental because it gets to the heart of one of the most important behaviors in alternating current, that phase shift between voltage and current.
So let's just get straight to the point. When you have an inductor in an AC circuit, what's the deal with the voltage and current? Are they perfectly in sync, or does one get ahead of the other? The answer here is a real cornerstone for understanding how AC power works.
And here it is, the single most important takeaway. In what we call a purely inductive circuit, that's one with just an inductor and nothing else, the current always lags behind the voltage. And it's not by some random amount, it's a very precise 90-degree phase shift. Really, the easiest way to lock this in your memory is with this simple phrase: voltage leads, current lags. If you look at the two waveforms on the screen, you can see it plain as day. The voltage wave hits its peak a full quarter of a cycle before the current wave does.
So we know what happens, but why does it happen? Why does the inductor cause this delay in the first place? Well, it all comes down to this fascinating phenomenon called back EMF. It's basically the inductor's way of pushing back against any change.
Let's just trace the cause and effect here. First, that alternating current, which is constantly changing, flows through the inductor's coil. This, in turn, creates a magnetic field that's also constantly changing, growing, shrinking, flipping back and forth. Now here's the cool part. That changing magnetic field actually induces a second voltage right back into the coil. That's our back EMF. And its one and only job is to oppose the very change in current that created it. It's like this built-in resistance to change, and it's this constant fight that makes the current fall behind the voltage.
Okay, so we know the inductor fights back, but how can we measure that opposition? It's not the same as the simple resistance you see in DC circuits. In the world of AC, this kind of opposition gets its own special name. We call this opposition inductive reactance, and we use the symbol X with a subscript L to represent it. And even though it's a different concept from resistance, we actually measure it in the very same unit, ohms. This is the number that tells us exactly how much an inductor is going to push back against the flow of alternating current.
And here is the formula we use to calculate it. Inductive reactance, or XL, equals 2 times pi times F times L. So let's take a second and just quickly break down what each of those variables means. So XL is the inductive reactance we're trying to find, measured in ohms. Pi is, of course, just the good old mathematical constant. F stands for the frequency of the AC supply, which we measure in hertz. And finally, L is the inductance of the coil itself, measured in a unit called the Henry.
Now, this formula shows us two really straightforward relationships. If you increase the frequency of the AC signal, the inductive reactance goes up. Same thing if you use a coil with a higher inductance, the reactance goes up too. This tells us something pretty important. Inductors have a much stronger opposition to high-frequency signals than they do to low-frequency ones.
Theory is great, but let's make this more concrete. We can run through a quick numerical example to see exactly how this formula works in practice.
So, let's imagine we have an inductor with a value of 0.1 henries, and we connect it to a standard 50 Hz AC supply. All we have to do is plug those numbers into the formula XL equals 2 times pi times 50 Hz times 0.1 henries. You run that calculation, and the answer you get is about 31.4 ohms. That's the specific amount of opposition that this inductor will provide to that specific AC signal.
Okay, so why does all this matter outside of a classroom or a textbook? Well, it turns out this phase lag and reactance have huge consequences in pretty much every real-world electrical system you can think of.
The truth is, inductors are absolutely everywhere. They are the core component in electric motors and transformers. They are essential for our power grids, and they're used to build all sorts of electronic filters and chokes. The behavior we've just been talking about is exactly what makes all of these technologies possible.
A perfect example of this is in a large industrial setting. Think about all those powerful motors and heavy machinery. They all act like giant inductors. This causes the current to lag behind the voltage for the entire factory's electrical system, which creates something called a low power factor. That basically means the system is inefficient, and power companies often charge extra for that inefficiency.
All right, we have covered a good bit of ground here. Let's do a quick recap of the most important points to remember.
Okay, first and foremost, in a pure inductor, the current lags the voltage by 90 degrees. Second, the opposition an inductor presents to AC is called inductive reactance, or XL. Third, you can always calculate it with the formula XL equals 2 pi FL. And finally, just remember that the reactance gets bigger as you increase either the frequency or the inductance. So, now that we've got the inductor figured out, where do we go next? Well, in our next explainer, we're going to tackle its counterpart, the capacitor. And you're going to find that its effect on voltage and current is the complete mirror opposite of everything we've talked about today. I'll see you then.